Hello students, this is the 7th lecture of the series on machine learning. If you find it helpful, please like this video and subscribe to my channel. In this lecture, we will cover 4 different types of metrics or errors that we can use to evaluate a regression model. First, we will cover these 3 fundamental types of errors that are used to evaluate regression models. Then I will show you a limitation of these 3 types of errors with an example. And then we will see how a different and more advanced type of error, which is the mean squared logarithmic error, can solve that limitation. So let's start. Mean absolute error is based on the absolute difference between the actual target values in the dataset and the predicted values by our regression model. Consider a problem where we are using a regression model to predict the number of calories burned by a person according to the number of steps taken by that person. So, consider this data set where the first column contains the number of steps taken by that person. This is the predictor variable and can be represented with an X. The second column is the actual calories burned by that person, which is the actual value of the target variable. It is represented with a Y. The third column is the number of calories burned by that person as predicted by our regression model. So the predicted value is denoted by a Y hat. Now here, this is the equation of mean absolute error. Look at this equation. N refers to the number of data points or the number of rows in the data set. In this data set, there are 1, 2, 3, 4, 5 rows. So, N is 5. Next, here Y is the actual value of the target variable and Y hat is the predicted value of the target variable. This is the absolute difference between the actual value and the target value, and the summation sign means that we want to sum up the absolute difference between the actual value and the target value for each row in the data set. So I will now calculate the mean absolute error for this data set. So let's see. The absolute error is represented by this. It is actually the difference between this and this, the absolute difference, so which is 10, 5, 10, 5 and 100. As I said, the summation sign means that we have to sum up this term for all the values in that data set. So let me complete this formula by plugging in the values. So if you see that this 26 is the value of the mean absolute error. I want you to notice one important point in these values. If you look at the absolute error, this absolute error for the last row is much bigger and much beyond the range of the other 4 absolute errors. So such a value that is much beyond the range of all the other values or most of the other values in the data set is called an outlier, and it is a property of mean absolute error that it works well with outliers. Mean squared error is based on the square of the difference between the actual value and the predicted value of the target variable. This is the equation of mean squared error. It is different from mean absolute error in that the difference between the actual value and the predicted value of the target variable is squared. This is the same data set as before, where this is the predicted variable, this is the actual value, this is the predicted value. So let's first calculate the squared error across each row in the data set. Now, because there are 5 rows in the data set, the value of n is 5. So let's calculate mean squared error by plugging in these values. So the value of mean squared error is 2050. So again, this value here is the outlier, which is too big and too beyond the range of the other values. But with squared error, it is growing exponentially big. So squared error is highly sensitive to outliers. The problem with mean squared error is that it becomes too large and it gets difficult to interpret it. So we need to make it smaller. We can take the square root of the mean squared error to make it smaller. And the resulting type of error is called the root mean squared error. Let me calculate it. So the resulting error is 45.3, which is within the limits or the scale of our data. Consider two cases of a regression model trying to predict the test score of a student. In the first case, the total test marks are 10. The student scored 9 marks, while the model's prediction was that student will score 1 mark. Now this is a very bad prediction, because when the total marks are 10, 1 is very different from 9. So the model is failing badly. But if we look at the squared error, the squared error is 64. Similarly, if we look at the absolute error, the absolute error is 8. Now come to the second case. The total marks are 1000. The student obtained 909 marks and the model had predicted 901 marks. Now the model is close to being accurate. Now the model is performing well because 901 is close to 909 if the total marks are 1000. So if we look at the squared error here, it is again 64 and the absolute error is again 8. So in both the cases, the absolute error and the squared error is the same, whereas what we want is that because in the first case the model did not perform well, so the error should have been greater, and in the second case the model performed very well, it is close to being accurate, so the error should be minimal. But these two errors are the same. So this is the problem. The problem is because the absolute error and the squared error both actually consider the absolute difference between the predicted and the actual value, and they do not consider the relative difference. So to solve that problem, we have a different kind of error that is called the mean squared logarithmic error. And this is how we calculate that error. We add 1 to the actual value of the target variable and take log. Then we add 1 to the predicted value of the target variable. Then we take log. Then we take difference, subtraction, and then we take the square. So we get the logarithmic error. Now, when we calculate the logarithmic error in both cases, the logarithmic error in first case is 2.59, whereas in the second case it is minimal, which is 0.024. So, logarithmic squared error is performing much better here. This is the same dataset that we use to calculate mean absolute error and mean squared error. This is the equation of mean squared logarithmic error. So, to calculate this error, we can find this term for each row against the predicted and the actual values of the target variable. So once we have all these, we can sum them up and then put them in this formula and put here n is equal to 5 because there are 5 rows in the data set. N is 5. Once we put them here, multiply them with 1 by 5, we will get this. So 0.26743, that is the mean squared logarithmic error.